Welcome to the next video in a course in real analysis. This is lesson 5.1. We'll be doing exercises about some of the algebraic properties of suprema. So before we get going, let's establish some notation. We'll be talking about things in the context of an ordered field, and we will define A plus X to be the set of all A plus every element of X, put briefly. And a X is A times every element of X, and so on. X plus Y, right? So if X and Y are two sets, then we form the set of all sums between X and Y, and XY is the set of all products. So I think that notation is fairly clear, so let's go on to the exercises. So we're going to let X be some subset of F, and we're going to take A an element of F. And by the way, we should also assume that X is non-empty and bounded above. So the set of upper bounds is not empty. So under all those assumptions, we will prove this fairly believable equation that sup A plus X is the same as if we pull the A out and plus sup X. Now, if A is a non-negative number, then the same kind of thing holds when we're talking about sup AX, although when we have a negative number, then in fact when we pull A out of the sup AX, it flips it to an infimum. Okay, second exercise, we'll take two sets. Again, we should stipulate that they are non-empty and bounded above. So assuming that, then sup X plus Y is always sup X plus sup Y. But in the case where we assume that they are sets of positive numbers, right? So basically what I'm saying is that X contains no non-positive number and Y contains no non-positive number. Under that assumption, we can say that sup XY is equal to sup X sup Y. And that's the last exercise in this set. So if you want to solve these for yourself, then stop the video, please, write the exercises down, and solve them yourself, and compare your answer with the solutions that I'm about to give. So here we're going to start by proving the first equation. And it's worth, if you're new to these proofs, wondering how are we going to approach this? Well, we could start by trying to show something about the left-hand side, or we could try to show something about the right-hand side. Now, I'm going to say that we're basically going to take the right-hand side and demonstrate that it has the properties of being an upper bound and the least upper bound for the set A plus X. So why, right? I mean, I feel like when I first learned this material, I wouldn't have known to start approaching the problem that way. And so to give some indication for why that's a good way to approach the problem, this thing over here is the sup of some set. And that's, in a sense, kind of all it is, or like sort of the outermost operation, you could say, is to take the supremum. And so because it is like that, then it means that whatever we have over here, we can just show that it has the properties of the supremum. So I guess what I'm mostly getting at here is that when you're trying to show that, you're showing some equation that has sups in it, if one side of the equation is a simple sup, it is a sup over just a single set, then probably you want, I can't promise this always goes this way, but a good rule, good guidance is to try to show that the thing on the other side of the equation has the properties of the supremum for whatever set is here. So that's some developing some instinct about how to approach proofs like these generally. Okay, if that's what we're doing, we're going to show that this thing has the properties of the supremum of this set. Then we're going to have to show that a plus sup x is an upper bound on that set, and also a plus sup x is a lower bound on the set of all upper bounds of a plus x. But before going any further, we want to even just ensure that this thing on the left, this sup of a plus x, even exists, right? We want to know that it is meaningful to talk about sup a plus x. And to do that, we have to ensure that it is non-empty and bounded above. Now, it is non-empty because x is non-empty, and therefore we will have some element, and a plus that element is in a plus x. So it is non-empty. That is very easy to see and to show. But let's now talk about bounded. So let's take something that is an upper bound of x. And remember, we assumed that x was also bounded above. So we know that this alpha in the set of upper bounds of x, that alpha exists. Now we're going to show that, or we're going to try to find some upper bound on the set a plus x, and therefore we should pick an element out of the set and demonstrate that it pre-seeks whatever we think the upper bound is. Now, if we have that alpha is an upper bound of just plain x, it makes sense to guess that alpha plus a, or a plus alpha, is the upper bound, or an upper bound, on a plus x. So this is what we're going to try to show is an upper bound on a plus x. Well, so we pick an element, right? We pick this a plus z out of the set. That means z is an arbitrary element of x, little z is an arbitrary element out of x. And because alpha is an upper bound on the set x, then that tells us that z pre-seek alpha. So from this equation, we can just add a to both sides, and we now have that exactly what we wanted to show, a plus alpha. We were trying to show that that's an upper bound on a plus x, since we just showed that it is, let's just say greater than or equal to a plus z, no matter which z is chosen from x, then that's it, right? That shows that this thing is an upper bound on the set. So that part is done. Okay. So now we move on to what we were talking about before. We're going to show that this a plus sup x, we're going to show that it is an upper bound of the set a plus x. I am just denoting this part by the triangle symbol just to give us a little bit of like a name for some of the parts of this proof if we ever need to refer to the parts. So anyway, okay, so how are we going to prove that this thing is an upper bound on the set? Well, very much we're going to approach this like we did the step just a moment ago. We're going to take any arbitrary element out of that set. We know that by definition, z is in the set x, and therefore z pre-seeks sup x. And we can add a to both sides, and we get exactly the inequality that we were hoping to demonstrate. So that shows us that a plus sup x is an upper bound on a plus x. Okay, using a square to give kind of a symbol for the next section. In this section, we're going to show that a plus sup x is a lower bound on the set of upper bounds of a plus x. So that's the rest of what we need in order to show that this thing is a supremum. Now, how do we do that? Well, we pick some element from the set, but in this particular instance, when we pick an element from the set, we're picking an element from the set of upper bounds of a plus x. And so that we're going to call alpha. So alpha is an upper bound on the set of a plus x. We're trying to show that this a plus sup x is a lower bound on the set of upper bounds. So what that means is we need to demonstrate, right? Our goal right now is to demonstrate that a plus sup x pre-seek alpha. So, okay, how are we going to show that? Well, certainly we're going to need to use information about alpha. So if we pick any element a plus z out of the set a plus x, then because alpha is an upper bound on a plus x, that means alpha is bigger than a plus z. Now, where are we going from here? We're trying to reason about this quantity sup x, and that we know is an upper bound, and in fact it's the least upper bound on the set x. So probably a good idea is to try to solve for that element that is in x, right? So solve, in a sense, solve for z. So I'm subtracting a to the other side. And this demonstrates, right? So this inequality, since it is true for every possible choice of z, then that must mean that the thing on the right-hand side is an upper bound on the set x, right? So from this inequality, since it is an upper bound on every element in x, then it, well, is an upper bound on the set x. I had a little typo there, but scratch that out. And so then it follows, right? Since this is an upper bound on x, but sup x is the least upper bound, right? It is also a lower bound on the set of upper bounds of x. Since we have an upper bound on the set x, then sup x must precede it. So we get this inequality from the above. If we then just add a to the other side, we have now proved what we set out to prove. Because you can see this is what we said we were going to prove, and we now have exactly that. So we now know that a plus sup x is a lower bound on the set of upper bounds of a plus x. Okay, so because we have everything necessary to satisfy the definition of supremum, then we have that this thing is the supremum. So that finishes the first part of the proof. We're going to now move on to talking about the part of the proof that regards this multiple of A. And initially, we're going to assume that A is non-negative. As before, we should ensure that the set AX is non-empty bounded above. Of course, it's non-empty because X is non-empty, so whatever element x has, we can multiply by a. That's going to be in ax, and so that is non-empty. Okay, what about bounded above? Well, we're going to pick any upper bound for x. If we then also pick any element out of ax, which we'll call az, so z is an element of x. Well, since z is an element of x, alpha is an upper bound of x, so we get that z pre-seq alpha. And then this is where it's important to know whether a is non-negative or whether it's negative. Because we know it is non-negative, then when we multiply throughout, we maintain the direction of the inequality. And this shows that a alpha is an upper bound on the set ax, because that was an arbitrary element out of ax. So there it is. We have now confirmed that ax is non-empty bounded above, and therefore its supremum must exist. So we've basically demonstrated that it makes sense to even talk about sup ax, and now we'll go on to prove the inequality regarding it. Now, let's actually split off the case where a is equal to 0. If a is equal to 0, then ax is 0x, and that means we multiply every element by 0. Well, that means that no matter what x is, 0 times x is just the set containing 0. So it's just that singleton set. And then its supremum is equal to 0. Okay. On the other side, if we had, whatever this sup x is, if a is equal to 0, then we take whatever that number is, we multiply by 0, and we know that the result is 0. So what we've basically just talked through is that when a is equal to 0, the left-hand side is equal to 0, the right-hand side is also equal to 0, and so the equation is true in the case where a is equal to 0. That's the relatively trivial case, so the proof gets more challenging and interesting when we move on to assume that a is not 0, which is to say that a is strictly positive. As before, we have two things to show: that a sup x is an upper bound on the set ax, and then later that it is a lower bound on the set of upper bounds. But just to address the first part, we're going to show that it's an upper bound. So we're going to take an arbitrary element. We know that since z is in the set x, then therefore sup x is bigger, and we can multiply throughout by a. That preserves the direction of the inequality because a is positive at this point. And what this then demonstrates is that a sup x is an upper bound on the set of all az, which is to say it is an upper bound on the set ax. Okay, so that concludes this pentagon part of the demonstration. So next we're going to move on to hexagon, and that is the part where we demonstrate that a sup x is a lower bound on the set of upper bounds. So as before, we're going to take an arbitrary upper bound, call it alpha, and we're going to pick an arbitrary element out of ax, so it follows immediately that, element out of ax, which we're calling az. It follows immediately that az pre-seq alpha. Okay, now this is where it's important to know that a is not 0. Because a is not 0, we can then infer that, we can divide both sides by a. So we get that z pre-seq alpha over a coming from this inequality. This demonstrates that alpha over a is an upper bound on the set x. Because it's an upper bound on the set x, it must be greater than the least upper bound. And so we get this inequality. If we then multiply by a, we get this inequality, and effectively that shows exactly what we set out to prove, which is that a sup x is a lower bound on the set of upper bounds, because this was an arbitrarily chosen upper bound of ax. So there we have it. Then in this case, we know that a sup x satisfies all the properties that define the supremum of ax. So that part is done. Now, I'm not going to show the part where we prove it when a is strictly less than 0, that is to say when a is negative. It's a good exercise, especially since you've just seen me do the part where a is non-negative. Then you should be able to do similar moves to prove the case when a is strictly less than 0. Just notice that you're going to need to guarantee that the set is non-empty bounded below, and you're going to have to, multiplying by a negative is going to flip the direction of inequalities whenever that comes up. So you're going to have to be careful about that. But it should not be too hard, especially given that you've just seen me do this. So I'm going to leave that to the viewer. Okay, we move on to the second exercise, which regarded sup x plus y, showing that that is sup x plus sup y. So based on what I said at the beginning of the first exercise, it is hopefully clear to you how we ought to approach this problem. We ought to take the thing that is a sup of some given set and show that whatever is on the other side of the equation, it has the properties of being the sup of that set. So we're going to take sup x plus sup y and show that it is an upper bound on the set x plus y, and that it is a lower bound on the set of upper bounds of x plus y. Okay. As always, we should first guarantee that it is non-empty bounded above. we are assuming here that both x and y are non-empty, and therefore the sum x plus y is non-empty, right? You'll have just some element in x, some element in y. Their sum is going to be in x plus y. So x plus y is non-empty. That is very easy to see. We want to show that it is bounded above. Well, take an upper bound for x, because we're assuming x is bounded above. Take an upper bound for y. Add them together. It should be very, very easy to demonstrate that what you get when you do that is an upper bound on the set of x plus y. I guess I just said it where you took any arbitrary upper bound, but since sup x and sup y are upper bounds, you could, if you wanted to, specifically talk about this particular sum of upper bounds, right? So since this is an upper bound, this is an upper bound, then this choice of a sum of two upper bounds will work. But it's up to you how you write, so you could prove it either way. Anyway, those details are not terribly important. So let's move on and talk about triangle here. So we're going to show that this number, sup x plus sup y, is an upper bound on the set of x plus y. To do that, we're going to pick two arbitrary elements, one from x, one from y, and we'll be thinking about showing that sup x plus y is an upper bound on that, on a plus b. Well, certainly, since we know that a preseq sup x, b preseq sup y, then when we add these together, we get exactly the inequality that we're trying to accomplish. And so that is done. There, we know that it is, right, sup x plus sup y is an upper bound on the set x plus y. Okay, moving on, we'll show that sup x plus sup y is a lower bound on the set of upper bounds of x plus y. To that end, we pick an element out of the upper bounds on x plus y. Let us temporarily fix a particular choice of a, and then think, corresponding to this choice of a, about the various choices for b in y. Now, with this fixed a, no matter what b we pick, we know that alpha is going to be is going to satisfy this inequality because alpha is an upper bound on x plus y. We can move the choice of a to the other side so that we get that b preseq alpha plus a. And that demonstrates that whatever this alpha minus a is, it must be an upper bound on the set y, right? Because b was an arbitrarily chosen element out of y. So whatever this fixed element alpha minus a is, it's an upper bound on the set y. Well, since alpha minus a is an upper bound on y, then it must be greater than or equal to the least upper bound, which is to say sup y. So we get this inequality. Now we can rearrange this to put a on the left side, subtract the sup y over to the right-hand side, and this is true for every possible choice of a, right? I mean, everything that we did above was true no matter what a is. So now this equation must be true no matter what a is, and a is an arbitrary choice of element from x. Well, then that just means that alpha minus sup y must be an upper bound on the set x. Okay, well, if it's an upper bound, then it must be greater than or equal to the least upper bound. So sup x preseq alpha minus sup y, add sup y to the other side, and we have exactly what we sought to show. All the properties of being the sup of x plus y have now been confirmed, so the proof is complete. So now we move on to the final part of the final exercise, which is to consider when these are sets of positive numbers. And when these are sets of positive numbers, we're going to demonstrate that sup xy equals sup x sup y. We'll show that the thing on the right-hand side is an upper bound and a lower bound on the set of upper bounds, put very briefly. But as usual, we should demonstrate that this is non-empty and bounded above. Well, since x is non-empty and y is non-empty, then we can take some element from x, some element from y, multiply them together, and that gets us an element of xy. And so there we have it. It's non-empty. We can show that it is bounded above, and in particular, if we want to point to sup x sup y, it's pretty straightforward to demonstrate that sup x sup y is an upper bound on the set xy. But now we want to show that sup x sup y. Well, I'm actually now realizing I gave the proof right here. So there it is, right? And it's very straightforward. So pick any element out of xy. We know that A pre-seek sup x, B pre-seek sup y. And so therefore, AB pre-seek sup xy, making this an upper bound of the set xy. Okay, next we show that it is a lower bound on the set of upper bounds. So we take an upper bound. We also take an arbitrary element out of xy. We know by definition that AB pre-seek that alpha. We can divide by A, and that is justified because we know A is strictly greater than 0. So its inverse exists, and when we multiply across the inequality, it preserves the direction. So that's what, kind of why we needed to assume that these were sets of positive numbers to make all of this work out. So, and by the way, there is a generalization of this where the sets don't have to be only positive numbers, they can be non-negative numbers, but the proof is a little bit more tedious. But if you already know this result, then generalizing to the sets of non-negative numbers is really easy. You can use the result that we're talking about here to give an easy proof for the more general result. So anyway, we now know that we can divide to the other side by A due to compatibility, and this makes alpha over A an upper bound on the set y. Because it's an upper bound, it must be greater than or equal to sup y. We can multiply the A back to the other side. If you think back to how the plus version went, we kind of, did very similar moves, just using pluses and minuses and so on to move things around in a similar way. But at this moment, what we want to do then is we want to divide sup y to the other side. But for, although it is a set of positive numbers and you would expect perhaps sup y to be positive, we probably ought to give a clear, rigorous explanation for why that is true. Well, since y contains a positive number, then sup y must be positive. Well, if you want to elaborate that, and you certainly could elaborate that a bit more, whatever the positive number is in y, sup y has to be greater than or equal to that. So you would, if we call that element, what do we want to call that element? We'll call it C, right? So if C is in y, then we have that C is bigger than 0, and sup y is greater than or equal to that, so this gets us that sup y is positive. So anyway, okay. So now that we know that it's positive, and therefore we can divide by it, and when we do, it does not change the direction of the inequality, then we get this inequality that now tells us that, that alpha over sup y is an upper bound on the set x. Therefore, it must be greater than or equal to the sup x, multiply the sup back to the other side, and this shows the lower bound property that we were trying to demonstrate this whole time, and the proof is now complete. And finally, I'd like to give an invitation to ask questions. If anything in this video was confusing, or if anything in the related sections of the textbook were confusing, then please leave a comment, as clear a question as you can, and I will either answer it in the comment section, or if it's a substantial thing, then I may make a video about it and include it in the playlist.